Properties of linear functions. So, in order for something on a graph to make a straight line, we noticed something about how things change. And the thing that we're going to notice is that every time your x value changes by a certain amount, so as we go 1 over in the x value, this one goes 1 up. Then we do it again, 1 over, 1 up. 1 over, 1 up. And the amount that we go up always stays the same, and the amount that we go over always stays the same. If that is constant, then we will always draw a line. So a linear relation is called a linear relation because it makes a straight line. And we call this change, that's always the same, measuring how much it goes up divided by how much it goes across, as the rate of change or slope. And in math, we use m for slope. Anybody know why you use m for slope?
Oh, my brother taught me that. And
Are you learning slope?
Yeah, we were just doing slope and
Well, that's perfect.
this is like the y
all lining
equals
Y equals
mx
mx plus b. We're going to get into that's our whole next unit.
plus.
Now the
Oh my
m,
God.
this is true. The m, we use m for slope because what has slopes?
M.
Something that starts, it actually comes from the French word for mountain. Not the English word for mountain, but they both start with M. So when you think about things that have steepnesses, straight lines like that, they thought of mountains, so they use M for slope. There we go. And we measure our slope as looking at the change in the y variable. How much is the y variable changing, and how much is the x variable changing? And this can be simplified to the change in the y we call the rise, how much is it going up or down, and the change in the x we call the run. So slope is often referred to as rise over run, which is the change in y divided by the change in x.
I mean, we literally like
Just learned this in science. This is perfect. Science is probably mad at math because you went to science and you hadn't learned it yet in math. And math is happy now because you just learned this in science.
Karen, can I go to the
So Haley, this is exactly what you just said, that you can write a line as y equals mx plus b. X is the independent variable, y is the dependent variable, m is the slope, and b is always your y-intercept, where it crosses the y-axis. So we are going to be working with this equation a lot, and after grade 10, it will be assumed that you know how to do this like really, really well in grade 11 and grade 12. So knowing how to graph lines and how to work with lines. In fact, our whole next chapter looks at it more in depth. This chapter is relations and functions generally, and next chapter is like specifically what are all the things you can do with lines. So if we look at the graph at the bottom of the page, and we look at the numbers, going from point to point, we're always going 100 to the right and 20 up.
Wait, can we go back to the next one?
Yeah, can we?
So does this make sense if your rate of change or your M value is your change in your dependent, your change in Y, that's the rise, that would be 20, over the change in the independent, the change in X, which is your run, we would get 20 over 100. We could simplify that if we wanted to, as a smaller fraction or as a decimal. So apparently, according to this, it costs you 20 cents for every kilometer if you rent a car. What happens if you don't drive any kilometers in this case? Should it be free? No. That would be nice. But it's not. Well, how much does it cost you if you don't spend or don't drive at all? According to the graph. 20 cents? No?
0.2
No. If you don't drive anywhere, how much is it going to cost you?
$60.
$60. Look on the graph. If you don't drive anywhere, your driving would be 0, but on the graph, it's still at $60. Okay? That they charge you $60 to rent the car, whether you drive it or not. And then each additional kilometer you put on there costs you more.
That's cheap.
That is pretty cheap. $60 to rent a car? Especially if you don't drive it around too much. So we would say that the rate of change is 20 cents per kilometer. And what does it mean? That means for each additional kilometer that you drive, the cost increases by 20 cents. So we could make then a formula using the y equals mx plus b.
We're gonna draw that photo.
The initial amount is your y-intercept. That's when you haven't drawn any. That's going to be $60. B is your independent variable. That's like using the x, but since we're driving in distance, we might put the letter D. Your M value, your rate of change, we figured out to be 0.20. And your Y value, in this case, was cost. So the letter C makes sense for that. So here we have a relation. One of the ways that we could get a relation is a table of values. You have your x value, or your, in this case it's t, but this would be your dependent value. This would be your, this is your independent value, and this would be your dependent value. Does this make a straight line? Well, we could draw a graph to find out. That could be one way to tell if it makes a straight line. The easiest way, though, to see if something is a straight line is to check every time your dependent variable increases, does it increase by the same amount? Okay? So every time we're going here, it's going up by 20, up by 20, up by 20, up by 20, up by 20. If your dependent variable also increases by the same amount every time, it'll make a line. But if it increases by different amounts, which this one does, right? Goes up by 1, then it goes up by 2, then it goes up by 4, then it goes up by 8. This makes it not a linear function, or not a linear relation. Quickly, can you see that the graph would have also worked on my graph? I would put time down here. 20, 40, 60, 80, 100. And maybe I'll go 5, 10, 15, 20, 25, 30. 5, 10, 15, 20, 25, 30. When you're drawing your graph, your scale has to increase by the same amount on the y and the same amount on the x. But it doesn't have to be the same on both. Notice my x's are going by 20s, my y's are going by 5s. If I would graph this, can you see that you have 0, 1, then 20, 2, 40, 4, 60, 8, 80, 16, and 100, 32. Is that a straight line? No. So it would have to be a perfect straight line in order for it to be a linear function. But we can just check it by looking at the values. So let's look at the next one. Are we going up by the same amounts here? We're going up by 60s every single time. What about here? Yes, we're going up by 3 every single time. So because we're going up by the same amounts for our y, the same amount for our x, the change in y is always 3, the change in x is always 60, our slope would be 3 over 60, and this would be a linear function. So the next thing we're going to do is we're going to look at some of the equations that form straight lines. Most of them will be in y equals mx plus b, but there are 2 special equations that are just x equals and y equals. Now, the x equals minus 2 graph. If this is our equation, to draw the graph, they're basically saying x is always negative 2. Can you tell me a point on this graph where the x value is negative 2? Give me the y coordinate, for example. The x value has to be negative 2. Can you tell me a point on the graph, anywhere on here, where the x value is negative 2? Pointed, what would you call that point? Negative 2, comma. Is there some point on here where the x coordinate is negative 2? Yes. What? Can you give me an example? Negative 2, comma 1. Negative 2, comma 0. Someone said another one. Negative 2, comma 1 would be there. Negative 2, comma 0 would be there. Can you give me another one? -2, -4. That would be there. What kind of straight line do you think this is going to make? A vertical straight line. If the x value is always -2, you get a straight line up and down. Can you see that every single point on that straight line would have an x coordinate of -2? Okay? Right? I pick a random point, even decimals. You're like, ooh, I've got -2, 3.5. That is on that line. Now, this is sometimes confusing for students because what do we call this axis, the x or the y-axis? We call this the y-axis. Okay? So students like to write this equation as y equals because they already think the y-axis is up and down. Okay? That's a mistake. What you have to think about is if I plot any point on this vertical line, what stays the same? The x value is always -2. Technically, the equation for the y-axis is x equals 0. The y-axis, every single point on the y-axis has an x value of 0. So this is a special one, a vertical line, x equals. Non-special ones look like y equals mx plus b, or can be rearranged. So if you had this and wanted to draw the graph, some of you in your studying have already figured out it's easy to go from here to a table of values, and then go from your table of values to your graph. Independent first, dependent second. Could you tell me one point that has to be on this graph?
0 and 5.
0 and 5. Can you, 1 and 6.
Negative
2, 7, negative
-2 and 3.
-2 and 3. So do you see that you could pick any x value you wanted, and then you could find the y value that goes with it. Now, when we go to graph this, we have 0 and 5, 1 and 6, 2 and 7, -2 and 3. Do you notice they make a straight line? And you're going to find out that any equation that has one y, one x, adding and subtracting anywhere will always make a straight line. Now, we technically need to label some of these points, because if you don't label your points, you don't have a scale. All right, we'll do 2 more. This is the other special one. We did x equals -2. What do you think is going to happen if the y value always has to be 5? It's going to be a horizontal line. Can you see that you could have this point, 0, 5. You could have this point. You could go over here and do y equals 5 the same. The y value always has to be 5. How many points could you graph? Millions of them. Really easy. And if it's always 5 for the y value, you will get a horizontal line. So if you think about your x-axis, there's a horizontal line. Can you see that the equation of the x-axis would be y equals 0? Because every single point on your x-axis has a y value of 0. And the last graph that we're going to do today, this one is not a line, because we have a y But we don't have just one x, we have an x squared. So what is this going to look like? We're not sure. We know that it's not a straight line. We might have to do a bunch of points to really figure this out. Its shape. Okay. Tell me a point you could plug in for x. Easy mental math. What would be one of the easiest ones to do? 2? Well, then you have to do 2 squared. Get 4 plus 5. You get 9. That was pretty easy mental math, but I think you could pick a value that's even easier than 2. 1. Okay. Because 1 times 1, maybe a little bit easier than 2 times 2. You would get 6. Is there one even easier than 1? 0. You get 5. So far, well, 1, 2, 3, 4, 5, 0, 5, 1, 6, 2, 9 is too far up. Can you find me another point that is actually on the graph?
-1.
-1. What would happen if you did -1?
-1 squared is 1, plus 5 is 6.
-1 squared gets 6.
Broken. Not linear.
It makes a U-shaped graph that goes up forever. If you did more points, you'd see even more. And do you see that whenever you put in a negative number, like if I put in -2, I also get positive 9. And so there's a bit of symmetry in this one.